Okay, so we'll talk about some shaders and well in
I don't
context.
see your screen.
Oh yeah, thanks. Mm. 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 Okay. You can see the code?
Yeah, it's beautiful.
Thank you. I agree. So okay, we'll talk about some shaders in context of OpenGL mainly, but I'll use one of examples in our Nabla graphics engine. Well, when you will work with some code and writing your own shaders and playing with graphics in general, I recommend you using this our engine because it simplifies a lot. So well, you won't have to deal with a lot of GL calls, and you have this, let's say, pretty API and less code to to write.
Okay.
So yeah, I've chosen this.
Good selling points.
Again?
Good selling points. Let's go.
Yeah. So there you go. Okay, I've chosen some example that I think will be a good example for here. We're using actually Vertex and Fragment Shader, which are pretty let's say basic shaders that you will use ever. Like Vertex and Fragment Shader, you will always pretty always you'll have to write. And just as well, I'm using here a compute shader, which is well, we'll get to that, but compute shader is I think it's the most useful thing to know in graphics in general, because actually using compute shader you can emulate actually anything you want, because it gives you much more flexibility. And well, you've got from me some materials about compute shaders, and well, in context of OpenGL, but but not only, because well, in OpenGL, it's Vulkan and CUDA, etc. It's very similar APIs for compute. So okay, here we have this example. This is actually a particle system that's well, I have 1 million points and some gravity points. That's how I called it. Some gravity points, and I'm using obviously Vertex Shader to well, actual geometry. So those points you can see on the scene, and simple Fragment Shader to draw them on screen, and compute shader to compute physics. Let's call it physics, very basic physics, but yeah. So computing velocities and accelerations of those particles or points, if you wish. I can. Oh. You see still just the code, yeah?
Yeah, if you want to show me your whole screen, when you want to share, you've got
like an option to choose between applications and screens. Do you see that?
Check. Wait. Applications. Oh yeah.
And screens. And here you can choose your screen.
Yeah. Okay.
All right. Great.
So I've launched RenderDoc, which you know what RenderDoc is, or did you?
Yeah, I do.
Okay, nice. So we'll probably use this during the lesson, but just now. Oh, here actually it shows some stages from DirectX shader pipeline. But yeah, Vertex Shader is in the very beginning of the pipeline. Well, in the very beginning is this some input assembler, something like that. So actual geometry that goes into Vertex Shader, and Vertex Shader is responsible for manipulating on geometry, but in terms of vertex. That's why it's called Vertex Shader. So in Vertex Shader, let's go into this example's Vertex Shader, and how it looks is well, there's some that's engine specific code. This actually just a code that fixes a bug in AMD drivers that's well, related to this low major qualifier. Turns out that AMD doesn't really care about this, and it fetches matrices from buffers without caring about this row major qualifier. So your fetched matrix turns out to be transposed. Yeah. So well, anyway, back to the subject. Vertex Shader operates on geometry, but in terms of vertices. So in OpenGL you specify vertex buffers, which gives vertex attributes, and along with those buffers you specify the formats and formats of those attributes, and well, how much of them there is in buffers. That's actually during the actual draw call. Well, and other data like offset where attributes start in the buffer, and stride. So stride is this space between attributes of each next vertex. So well, Vertex Shader must have to know how to fetch each attribute of each vertex. So that's why you have to specify how the layout in the buffers in data. So well, graphics programming is a very low level thing. So yeah, and here you have just the position. So you've seen those particles that are represented by just single points. So each primitive, let's say. Well, you know what primitive is in context of graphics programming?
Pretty much any kind of shape.
Yeah, I think you can say that. Usually when you draw some meshes, etc., you operate on triangles. But in this case, I need just points.
Okay, so any kind of 2D shape, sorry.
Yeah, basically, yeah. 2D shapes that were transformed into 3D space, so they can show us as 3D meshes or points in 3D space, etc. Like in this case. So okay, Vertex Shader operates on those vertices, and basically what pretty always what Vertex Shader does is you have this MVP matrix. So MVP is matrix which actually contains three transforms, three other matrices. So model matrix, sometimes called world matrix, is just a transformation that that takes positions of vertices in some mesh you load it. So you have some model of let's say some character in your game, and obviously when an artist was modeling this mesh, there are those points are in some 3D space and have constant positions, obviously. So you wanna put this character in some place in your game, and this world matrix is responsible for transforming transforming positions of those local positions, local in terms of in terms of how actual mesh is created by an artist, and yeah, you so well, maybe you just need it specific place in your game without any rotation and scaling of this model. So then world matrix will be just a translation. So translation, by translation I mean that just some values are basically added to points loaded from the mesh file or something. However you got the data you wanna draw. And once you have your mesh in world space, coordinate system and space, I will use those terms in as synonyms. Okay. So once you have your mesh, so all the vertices of your mesh in world space, then you wanna transform that into view space. View space is a coordinate system relative to your camera. Relative in the context of this, that in view space camera is in point 000, so in the very middle of coordinate system, and is always directed in orientation of the axis. So well, that actually depends of if you have right or left-handed camera, but if I remember correctly, by default in OpenGL you assume that that camera will be oriented along the negative z-axis.
Okay.
And yeah, that's how we have those components M and V explained, and we have P left. So projection matrix is a matrix that actually transforms 3D coordinates onto screen. So actually applies things like perspective transform, let's call it, so that points in 3D space will look well reasonable on the screen, like you would like to say this in with your eyes. So projection matrix is usually perspective matrix, or there is this thing orthogonal transformation. So it's well, it's also used as a projection matrix, but it doesn't have this perspective thing. So well, you know how perspective works, and if when things are more far from you, and they're going into like converging into the middle point of the perspective, some horizon, however you wanna call it.
Let's say horizon. It's easier to, I guess, imagine it.
No, anyway, you just wanna have an idea what perspective matrix is for. Mm-hmm. And yeah, that's what basic vertex shader will usually do. And in this case, it does the same. And this is pretty basic example, so it's just perfect from our lesson about shaders. Another thing that more advanced that Vertex Shader can do is well, animations. There is some example in our engine, I believe in older API of our engine. However, you can look it up, and
okay.
There you'll see much more complex vertex shader that fetches transforms and bone weights of well, for animations. So it actually computes transforms of vertices of the mesh changing in time. So the mesh actually isn't static, and it well changes with time. So well, animations, yeah. So that's what you may use Vertex Shader for as well. Okay, and let's see into Fragment Shader. This is this is as simple fragment shader as it can get actually. So it just spits out the constant color. That's why you've seen those particles in just a single color. All of them are white. But obviously you can differentiate this color with some other data. Vertex stages of shader pipeline can communicate between each other. And so in this case, there isn't any communication.
Okay, sorry. So pretty much because I want to understand this from my point of view to just exactly know what's going on. So pretty much when you have a vertex shader, it's pretty much a shader that takes in as an input some vertices and actually calculates them. For example, you've got model with 30,000 vertices, so this shader takes them and sets some color or whatever on them. Am I right?
Set some color. I mean, colors. No, not really. But colors. Obviously, color can be. Color can be a vertex attribute, and well, we'll get kind of. However, you can just as well fetch some colors of the vertices from memory, right? Just like position, and pass them like to the next stage, next programmable stage. So in this case, we don't have any other stages in between. So another stage will be a fragment shader. So.
For example, here we are just declaring where's a certain position of a certain vertex, and that's it, right?
Yeah. In this example, yeah, exactly. But
what else, for example, can you do in Vertex Shader? What's a typical solutions problems that you have when you're working on Vertex Shader and you're actually doing a game or a movie or whatever, and you want to have some cool effects?
Well, everything that deals with geometry on the level of single vertices. So there's also geometry shader that actually works on primitives. So it doesn't. Well, vertex shader just knows a single point, single vertex, and that doesn't have access to any other vertices. But in case of geometry shader, it works on whole primitive. So in case of triangle, you can work on all 3 points, and actually geometry shader can create some, like, dynamically can create geometry.
Okay.
What you asked for, well, anything that works on geometry, but in terms of just single points. So, well, it's suitable for transforming vertices. I give you an example of scaling and animations. Yes, so that's really that's something that comes to mind really fast. That's not basic, but basic. It's advanced subject, but it's kind of basic use of Vertex Shader.
Okay.
Obviously, you can do the same in computer shaders. As like I said, you can.
So when would I want to use a compute shader and a vertex shader in this case? Let's say. Is there a difference, for example?
Well, difference is, well, compute shader Compute Shader is completely separated from the pipeline. So when dealing with Compute Shader, you can do actually anything. So Compute Shader is used when you have very specific needs, and you know how it will deal with performance. So you don't want to write just vertex shader which fetches data in I believe Compute Shader is you have much more control when data is fetched and how it's fetched and etc. So differences are there's you can't actually compare those things, yeah. You can't compare Vertex and Compute Shader because Compute Shader is very general thing, and it lets you do with GPU actually anything you want, and Vertex Shader is very specific thing that is placed in very specific place in the shader pipeline. So yeah.
Okay.
What we were talking about colors. Yeah, obviously color can be one of Vertex attributes. Obviously, just like in this case we have just position. And position is kinda very basic because you have to assign something to this GL position thing. GL position is actually output variable of Vertex Shader invocation. So you must assign something to this, because if you don't, then there is no point in calling Vertex Shader actually. But obviously you can have color attribute and then you can pass them into pipeline to the next stage. As I said, in this case we have just Vertex and Fragment Shader in the pipeline. So the next stage will be Fragment Shader, and you can do something like this. Something like, let's call it out attrib, whatever. And then you want to assign something to this.
Can you have any amount of in and out attributes in Vertex, geometry, and so on shaders and Fragment, or is there a pre-specified amount of inputs and outputs that you need to match, unless if you want your application to actually work?
Yeah, well, inputs to Vertex Shader is actually Vertex attributes, so that's why they are limited, and amount of Vertex attributes is obviously limited, but it's driver dependent, implementation dependent. However, in our engine we are limited to 16 of them, because that's a very common amount of Vertex attributes that will be supported among GPUs. Yeah, so that's why we have just 16 of them allowed. However, obviously I believe you can find drivers and implementations of OpenGL and or Vulkan, etc., that will allow you for more of them. But you can assume that the limit is 16. Yeah, you probably won't need any more than that. Probably, I never need it at least. So okay, passing data into next stage. So you declare this output point, let's call it, and here you declare some location. And so in this place in next stage, so in Fragment Shader you declare some input point with same type in a triple, let's call it.
I'll be right back, but you can continue because I suddenly have to fix something, but I will just rewatch it later, so go on.
Okay. And how long will it take you?
5 to 10 minutes.
Okay. Well, if you wish, we can just pause for those.
Okay, that would be great.
Okay, so let's pause. Okay, so where have we ended? Stopped or something? I believe we talked about passing data to next shader stages.
Yeah. So pretty much, we finished at my question that was, is there a limit to inputs and outputs in our shaders? Oh, there's pretty much no limit, but our as much as our memory can fit.
About outputs of
And inputs. Yeah, but I don't mean, for example, that we pass this vec3 focus, but I mean how many inputs we can, for example, create in Vertex Shader.
Well, I explained to you that there's a limit. Inputs to Vertex Shader are there are actually vertex attributes, yeah, because it's Vertex Shader, so amount of Vertex Shader inputs is limited by possible amount of vertex attributes, and you can assume that the limit is 16. However, you can for sure find implementations and drivers that will let you use more than 16, but probably you won't ever have to use more than 16, but because usually you can fit within like 6 or 7 with in most complicated cases.
Okay.
Usually it's just a position of the vertex, obviously, and then when normal vector of the vertex. This one you obviously have to have because you have to compute how light behaves on the surface. And and another one that is pretty basic is UV coordinates. So UV is coordinates of sampling the texture. But obviously you don't sample the texture. You can somehow, but you can fetch some buffers, etc. in Vertex Shader. However, UV coordinates you just pass next to the Fragment Shader, and there actually you actually use those UV coordinates to sample the texture. So okay, those are three pretty basic and most commonly used vertex attributes. However, yeah, how I, like I said, you can assume you have the limit of 16. Okay, back to the passing data around. So here we have declared this output point in Vertex Shader, and in next stage you have present in your pipeline you declare input point with the same type, and if you have this location specified, then you can use different name. However, very important thing, as you may have an idea, number of invocations and of Vertex Shader and number of invocations of Fragment Shader is two different things. Like Vertex Shader is has one invocation for each vertex in a mesh of a draw call you just issued from the CPU. And yeah, one invocation for the per vertex. And in Fragment Shader you have one invocation per pixel. That's well, let's go to the pipeline again. So here we have Vertex Shader that after those transformation with MVP matrix, you have points that actually go onto screen, and there you have this rasterize stage. You don't have like control on this stage. It's not some shader you can write code for. However, this is rasterizer that well, you have some points, some geometry that are, let's call it points that are connected, and rasterizer has to figure out what pixels will be used to actually draw the geometry on the screen. So when rasterizer figures that out, for each figured out pixel that will be used to draw the geometry, an invocation of pixel shader will be run. Yeah, so well, pixel shader, fragment shader, those are same things. So okay, number of invocation of vertex and fragment shader are totally independent from each other. So data coming from vertex shader are kind of interpolated. So you can have let's say you are drawing a triangle with some. This is pretty common example. You can oh yeah, that's pretty common example of showing this in most classes of this interpolation of data between vertex and fragment shader. In fragment shader you have just 3 invocations, so you have those 3 points, yeah, 3 vertices, and you have some let's say color attribute. Yeah, so in this case it's red, green and blue colors, but rasterizer decided those are the pixels that will be used to draw the triangle, and let's say you have the point in the middle of the triangle, so obviously you can't just fetch the data from one of the vertices. You have to somehow well actually interpolate the data, so that's why you have some weighted average of those colors for each of the pixels. Yeah, so that's why like the colors actually changes for each pixel. And yeah, that's pretty basic thing you can observe. However, not everyone understands it in the first try, I believe. Okay. However, in this case, we have this very basic fragment shader that just outputs a single constant color. I will remove those things because well, they're pretty useless now. Okay, so yeah, so there are just points. So geometry primitive is points. There's something there's declared. Let's go to actually code of OpenGL backend of our engine. So there you'll see actual OpenGL call that issues actual draw call, draw mesh buffer. So yeah, something. This is some enum that corresponds with Vulkan's enum for primitives types. Here it is, and we're translating this our enum into OpenGL value that will go into draw call of that actually draws the mesh. So here you declare the primitive type you will be using in shader pipeline, and so how the fetched from the buffers geometry will be drawn on the screen. Will it be those points interpreted as triangles or just points that will end up on the screen just as a single pixels, etc. So okay, in this case we have just points, and we have this vertex and fragment shader pretty explained, I think. And here we have this geometry shader that is well much less common thing, but it's useful in specific cases. So I wrote a little modification to this example to show you the usage of geometry shader.
Okay.
Okay. Here we have a geometry shader that will from each point of this well mesh, actually, because it's just a set of points, but still is well, in terms of a draw call, is still a mesh. What Geometry Shader does is, just as I said before, it operates on primitives, not just single vertices, and usually it's used to dynamically generate geometry. So, Geometry Shader is very costly to use, so try not to use it too much. However, it's very useful because you can dynamically generate geometry. So actually, you don't have to have this geometry in actual buffers. You can dynamically generate it. Yes. So in this case, I'm from each single point generating a square. So the particles won't be just single pixels on the screen, but they will be just squares that works with perspective. So the farther they are, the smaller they seem. Yeah. So they have actual and in this case, as I used a simple trick that, as I said, view matrix is a thing that camera is always in the middle of coordinate system and is oriented towards the z-axis. So if you want to generate a square, let's say, a square that will be always will work like a billboard. We probably know what billboarding is. So the square that is always faced on the screen, so it's not rotated, it's just facing the screen always. So I've edited I've modified the Vertex Shader a little, so it doesn't multiply the position with MVP matrix, but with just MV matrix. So in the next stage we have positions of vertex in the view space. So in the space you just create from these points, from each of the point which is primitive, you're generating 4 points that will be drawn as a square. Yeah. And then when you have the square generated, you actually multiply this with projection matrix. So actually this member of this tract is called MVP, but I've put here just a projection matrix. Here is the comment. So you don't forget. So yeah, about syntax, you must declare the input primitive that Geometry Shader with operate on, and obviously it has to match the primitive declared while calling actual draw call. So this thing I showed you just a few minutes ago. So in this case we have points. So with this declaration you declare that Geometry Shader will work with points, and here you declare an output primitive. So how what is actual primitive of Vertex Geometry Shader, and how those dynamically generated points will be will be connected with each other to form actual primitives. And you also declare the maximum amount of generated vertices in single invocation of geometry shader. So yeah, in this case I'm just generating this square, and you have a few functions that you can actually check it up later and read about it something yourself. However,
All right.
there is Emit Vertex, and if I remember correctly, there's also end primitive thing, I think. Primitive. You have but most importantly you have this Emit Vertex thing. So anyway, here you specifying the position, and also you can obviously have just other attributes that will pass to the next stage. So again, it will be Fragment Shader. Here we have just position, and after specifying position of the vertex you call this Emit Vertex. So the vertex is actually generated and passed onto raster, etc. Okay, and yeah, well, and basically geometry shader is used for the dynamically generating vertices geometry, and here you have you can have you have a choice, obviously. What primitive will be put here and here. You can read this specification of this, and much more detailed and let's say technical stuff, maybe let's call it. So well, you should read it anyway, so to work with geometry shaders. However, just to have an overall look on this thing is yeah. And another thing that's very useful actually, but again it's very costly to have geometry shader in the pipeline, is so-called layered rendering. So if you have layered rendering, you can read it later. However, you have this built-in output point variable of or something in geometry shader language of GLSL, and you can for each primitive declare the layer number, and when you have so-called layered frame buffer, so you can have layered frame buffer, and it actually means that you have frame buffer with layered attachment. So you have a frame buffer with texture attached to it in some attachment with multiple layers, and with layered rendering you can draw to to not just single one of them, but to all of them by declaring in Geometry Shader and declaring the layer, so that the pipeline knows when to which layer of the attachment of the frame buffer to draw the result, the geometry, the pixels, colors, etc. Or another data, whatever you wanna render into the frame buffer. Yeah. Okay, so let's see how it looks now. Okay, and you probably can tell a difference. You can see those are actual squares, not just
Squares!
not just single pixels. Yeah, so yeah.
Those are squares.
Yeah, that
Looks pretty cool though.
yeah, that's
It kind of feels like a Matrix movie where you're loading to this Matrix world or something.
yeah, a little. Yeah, so this this particular thing, I like to show this to people while teaching and showing some examples of graphics programming, because it's a very basic thing to do. Doesn't require a lot of knowledge to actually create this and write something like this. It will take not more than a few hours to create this, let's say, game or something. Sorry. But it's very pleasing to watch.
Yeah, it is. Looks really cool.
Okay. Actually, you can obviously pass more data around, and once I did something like this in not in our engine, but in pure OpenGL. Then some few years ago, when I actually started learning graphics programming and compute shaders, when I applied to the job I actually work with Met today, and then there I had also an attribute of colors. I believe it was computed in Vertex Shader, yeah, and then passed onto Geometry Shader just as a pass through, and yeah, so that colors of the particles can depend, for example, on the velocity of each particle, so it can look even cooler, yeah. So, well, this is a very simple thing, and you can play with it around and well, apply your own ideas, because it's very fun to develop. Okay, and well, actually we can capture this in RenderDoc, and okay. This is actually this shader pipeline where everything is run. So Well, there you see this AMD workaround that is just a pass-through function that actually fixes the bug of AMD.
But it's weird because it just takes a value and returns it.
Yeah, ask AMD. That's something with the shader compiler.
Okay.
Actually, this bug appeared like 7 or 8 years ago, and they still didn't fix it. It's ridiculous. Okay, so here we have those shaders of the pipeline. That's just it, and we have this GL dispatch compute call, and here you see, well, this is some stuff with well, this is related to translating Vulkans, because in our engine we use Vulkan dialect of GLSL to write shaders, but don't worry, that doesn't change a lot, just a few change names, and Vulkan have a few more features like this specialization constants, that those things are actually resulting from translations of Vulkan specialization constants into OpenGL capable stuff. So okay, here we have another shader that is used in this example is compute shader. In this case we have a very basic compute shader without any synchronization needed. It just fetches position and velocity from the buffers to actually operate on them, and from this with delta time, so the time of the frame, you can compute things dependent on time, such as change in velocity and like acceleration actually. And once we computed this without any need to communicate between invocations of compute shader and usage of shared memory, etc., without any synchronization, just write it back into buffers that will be used as a vertices in a local. As you see, this is how rendering of each frame looks. So this is GL dispatch compute that actually runs the compute shader. And next we have this draw array instant, but actually a thing that you wanna use, and mostly it will fit your requirements. Just GL draw arrays. GL draw arrays is used to draw geometry without usage of index buffers. So,
Okay.
So in case when you have triangles, GL draw arrays will draw the geometry like three adjacent vertices are one triangle. Yeah. In case of GL draw elements, if you have you are using index buffer, and in this case indices inside the index buffer are used to actually determine which vertices form a triangle, etc. So yeah, in case of going back to compute shader, pretty always you call it with GL dispatch compute. however, you also have the GL dispatch compute, another function that will let you take parameters of the dispatch from the buffer, so from the GPU memory. In this case, you put the parameters of the dispatch inside the call. So in this case, I have this 8K of work groups. 8K because each work group is in this case 256 invocations of compute shader, and 8K times 256 as is just 1 million, and so yeah, it operates on all the particles. Yeah, you probably, I believe you read already a lot of or at least a little about compute shaders, and
yeah, I did a bit.
Yeah, so you know what is work domain, work group, and well, basically this, but there is also subgroups, but this is more advanced and more technical stuff. Just API is actually very simple. There this work domain and declaration of how much work groups is in each of 3 dimensions of this work domain. So in this case, we can have just 1 dimension to be comfortable with this. You just very simple case. You just have those 8K of work groups, each one of 256 invocations, if each one of them does same thing. So obviously, while programming and compute shader, you obviously have to know which invocation actually you are in. So in this case, you have GL global invocation ID. This GLSL is actually already in OpenGL dialect of GLSL. So this is exactly how it's called in OpenGL. And in Vulkan, it just changed that instead of ID is index. So just that. And this is index of an invocation of compute shader within the whole work domain. So yeah, relatively actually global invocation ID. So there is no invocation ID in the whole work domain or whole dispatch with the same ID. It's unique and global. So you can, when you have something like this, you can use this global invocation ID to actually, for example, fetch some data from the buffer. So in this case, I'm using this global ID to fetch data of particles. Yeah, so API of compute shaders are very simple. However, yeah, there's this basically is a very useful page in the internet, this OpenGL wiki. That will tell you most of the at least the basic stuff. Nothing about some rendering and computation techniques, but about APIs, etc. a lot. So you have all the inputs you can have inside going into Compute Shader that built in. So those IDs, as you can see, they're three-dimensional because well, we have possibility of three-dimensional work domain. In this case, I'm just using one dimension, and the other ones are set to just one. Yeah, so they're defined. And about syntax, well, this is maybe not the most comfortable thing, but when declaring size of the work group, it has to be declared in actual shader code. So amount of work groups you can decide dynamically from the CPU side while calling GL dispatch compute, or the other one that takes the parameters of the dispatch from the GPU buffer. GL dispatch compute indirect. So, well, this is just one parameter, and what it takes is actually offset into buffer that is bound to some specific bind point in OpenGL, and then it takes the parameters of the dispatch from this buffer while reading the buffer like this struct. So it just takes those three unsigned ints from the buffer and treats the amount of work groups from this. So, well, you can decide a number of work groups dynamically, whether fetched from GPU buffer or declared while calling this GL dispatch compute from the CPU. But where was I? Oh, here. But how much invocation is within one work group is has to actually be declared like a constant in actual shader code, so it cannot be decided dynamically. Yeah, so here we have this Pilvik cross constant ID 0, which is well, here. So as I said, is 256 invocation per work group. Okay.
Okay, great.
And yeah, another thing about the Compute API and OpenGL, you can read up in OpenGL wiki.
Mm-hmm.
But well, just an API is very simple, and this more advanced and technical stuff, how to actually write optimal compute code, and which have very much to do with how actually GPU works, because as I said, compute shaders are very flexible and are you can say that they are much closer to the GPU and gives you much more flexibility than shaders within the shader pipeline. And I've sent you some time ago this article. I believe you already read it. about compute shaders and how they works. And well, we can obviously have another lesson about the subject. However, you have those this article, and about the API you have OpenGL wiki. However, yeah, I think that's it for the APIs thing.
Hey. Great. I mean, thanks a lot. Just
So yeah, I hope it was helpful, and
it was.
okay, nice.
So yeah, thank you for that. And I hope I see you in the next lessons. So cheers.
Okay,
Once
bye.
again.